Mount Merapi, is not quietly building a perfect new dome at its summit. It is doing something more unstable. High above central Java, thick lava continues to occupy the volcano's upper southwest flank. The material is so viscous that it cannot flow away like a river of molten rock. It piles up close to the vent, cools into jagged blocks, and repeatedly breaks apart under its own weight. During July 16th through July 22nd, 2020-26, Indonesian monitoring agencies recorded daily lava avalanches from Merapi's active dome on several days. 8 to 14 avalanches traveled as far as 2 kilometers down the Satpudi drainage. 14 more descended the Boyong drainage on July 20th, and a pyroclastic flow was detected 2 days later, and that is the current signal. The dome is not simply sitting at the summit because it is feeding the slopes below it, but the original title needs one correction, and this is not a completely new lava dome that appeared in 2026. Merapi's present dome building phase began after a major period of deformation in 2020-21. What is new is the continuing pattern visible now: repeated avalanches and changing summit morphology, and occasional pyroclastic flows produced by an active dome that remains mechanically unstable. And the danger is not the next small rockfall, it is what happens if a larger section fails at once. A lava dome collapse can transform a slow-moving pile of hot rock into a fast, ground-hugging pyroclastic density current. The collapsing blocks fragment as they fall, releasing ash and gas while gravity drives the mixture down steep valleys. And what begins as a failure at the summit can become a moving cloud of scorching rock fragments, dust, and turbulence. Merapi has produced this exact kind of hazard many times, and that is why the volcano remained at alert level 3 in the latest weekly report, with official exclusion distances ranging from 3 to 7 kilometers depending on direction. Those distances are not a prediction that a major collapse will happen on a specific day, and they reflect where the most credible current hazards could travel if the active dome sheds more material. The visible avalanche is only the first layer of the story. And the deeper question is why one collapse remains small while another becomes a dangerous pyroclastic flow. The answer depends on dome geometry, magma supply, internal fractures, gas pressure, the amount of material that fails, and the valley that receives it. And for documentaries that follow the physical mechanism instead of stopping at the dramatic image. Subscribe and stay with us. Merapi becomes much easier to understand once we stop thinking of the dome as a solid cap and start seeing it as a constantly rebuilt pile of hot fractured rock. Mount Merapi rises immediately north of Yogyakarta in one of the most densely settled volcanic regions on Earth. Its name is often translated as Mountain of Fire, but the volcano's characteristic danger is not usually a fountain of fluid lava. Merapi's magma is andesitic and comparatively viscous. As magma rises, pressure falls and dissolved gases begin escaping. The magma cools, crystallizes, and becomes even harder to move. Instead of spreading far across gentle ground, it is squeezed out near the summit as thick lobes and blocks. Imagine pushing cold toothpaste through a narrow opening. The material emerges slowly, but the pile in front of the opening can become steep because it does not flow away efficiently. Fresh lava pushes against older lava. The outer surface cools into a brittle shell, while the interior remains hotter and weaker. And that creates a structure with two conflicting behaviors. It is solid enough to stand high above the slope. It is fractured enough to fail without much warning. A dome can grow upward, outward, or into a steep lobe extending down one side of the crater. The direction depends on vent position, crater shape, earlier deposits, and where the growing mass finds the least resistance. At Merapi, the active dome on the upper southwest flank sends material towards several named drainages. The valleys matter because they become natural channels. A small avalanche may stop high on the volcano. A larger collapse can enter a drainage, remain concentrated, and travel much farther than it would over an open slope. This is why official hazard distances vary by direction. The mountain is not symmetrical. Neither is the risk. Every block that breaks away changes the shape of the dome. A collapse can remove an overhanging section and temporarily make the remaining mass more stable. It can also expose hotter material, steepen a new face, or remove support from the lava behind it. And the same event can reduce one weakness and create another. Fresh magma may then continue arriving from below, rebuilding the lost section. The cycle becomes extrusion, oversteepening, collapse, and renewed extrusion. This is the ordinary Merapi pattern, but ordinary does not mean harmless. During July 2nd through July 8th, 2026, the active dome generated 8 to 15 daily lava avalanches on several days. And the seismic network also detected 1 to 3 pyroclastic flows per day from July 2nd through July 6th, with individual flows traveling roughly 1.8 to 2 kilometers down western drainages. 2 weeks later, daily avalanches were still occurring, and that persistence is more informative than one dramatic video. It tells scientists that hot material remains available at the summit and that gravity is still removing it from the dome. Yet avalanche counts alone cannot tell them the size of the next failure. 10 small collapses do not add up to a guaranteed large one. A quiet day does not prove the dome is stabilized, and the monitoring problem is to identify whether the dome is merely shedding its surface or whether deeper deformation is preparing a larger portion to detach. Scientists watch this process with overlapping instruments because no single signal can reveal the whole dome. Webcams show rockfalls, glowing blocks, ash curtains, and changes in the dome's outline when weather allows. Thermal cameras identify hot surfaces and fresh collapse scars. Seismometers record the vibrations produced by rockfalls, explosions, magma movement, and pyroclastic flows. Electronic distance measurements track changes between fixed points on the volcano, and satellites can detect deformation or heat when clouds and darkness limit direct observation. Drone images add something especially important, and they allow researchers to build three-dimensional models of the summit, compare the dome from one flight to the next, and estimate how much volume has been added or removed. A dome may look nearly unchanged from one camera angle, while a lobe has thickened on the hidden side. A collapse may leave only a narrow scar at the top, but remove a large wedge farther down. Volume alone is not enough. A smaller dome with a steep, unsupported face can be more unstable than a larger dome resting inside a crater. A dome growing into a confined valley may repeatedly shed material in one direction. A dome that fills its crater can eventually spill over a rim and establish a new path. The location of fresh lava matters as much as the total amount. Fractures matter too. Some cracks are visible on the surface, others are buried inside the dome, where hot blocks, cooled crust, loose rubble, and older, altered rock meet. These internal boundaries can act like weak seams. Fresh lava pushing from behind can slowly open them until gravity takes control. Water can alter the structure over longer periods. Hot volcanic gases and hydrothermal fluids change minerals inside the summit, weakening rock that may still look solid from the outside city. And heavy rain can infiltrate fractures, add weight, and remobilize loose ash on the flanks. But a collapse does not need one simple trigger. It may follow continued extrusion. It may begin when the dome becomes too steep. It may occur after part of the supporting talus is removed. It may accompany an explosion that fragments the lava. Or it may happen through a combination of small changes that no instrument can isolate as the final cause. This uncertainty is why scientists speak in scenarios rather than countdowns. And the phrase, "the next collapse," does not mean a specific large event has been forecast. Merapi's active dome is already producing small collapses and avalanches. And the question is whether a future failure will involve enough hot material to generate a longer and more destructive pyroclastic current. To understand that threshold, picture the dome as a pile of blocks balanced above a steep channel. One block falls and stops. A larger slab breaks away and strikes the slope below. The impact shatters the slab, entrains loose fragments, and releases hot gas from the interior. The mixture accelerates. Dense blocks remain concentrated near the ground while ash rises into a turbulent cloud above them. This is a block and ash flow, one of the classic forms of dome collapse pyroclastic density current. It is not a normal landslide. The material can remain extremely hot. Fine ash reduces friction and allows the flow to move more fluidly than a dry rock avalanche. And the overlying ash cloud can spread beyond the dense basal path, reducing visibility and exposing areas outside the main block-rich channel. Valleys guide the strongest part of the flow, but they do not make the hazard perfectly predictable. A current can overtop a low ridge, it can split where drainages divide, it can erode loose material and grow. A larger collapse can sustain the current for longer, allowing it to travel beyond the distances reached by ordinary daily avalanches. This is where Merapi's topography becomes part of the eruption. The summit stands above a network of river valleys radiating toward inhabited land. Each drainage has a different slope, width, and history of deposits. Official recommendations therefore assign different exclusion distances around different sectors rather than drawing one simple circle. And during the latest July report, the public was told to remain 3 to 7 kilometers from the summit depending on location. The longer distances correspond to directions where dome collapse flows or lava avalanches are more likely to travel, and those zones are not permanent descriptions of every possible future eruption. They are operational boundaries based on the current dome position, recent activity, and modeled or historical pathways. If the dome geometry changes, the hazard direction can change with it. That happened during earlier phases of Merapi's activity. When new vents and domes redirected lava, collapse scars opened different channels and deposits altered valley floors, and the volcano repeatedly rebuilt the terrain that later controlled its flows. The summit is not a fixed machine. It is a moving structure that edits its own hazard map. A 2026 numerical study of Merapi's 2020 instability crisis shows how dramatic that structural change can become without ending in a catastrophe. From July 2020 to January 2021, the northwestern flank moved outward after magma pressurized a major fracture across the summit. The affected zone was about 1 kilometer wide and extended roughly 500 meters vertically, and measurements and modeling indicated displacement of around 14 meters, an extraordinary amount for a volcanic flank being watched in real time. Scientists feared a larger flank failure. It did not happen. The movement eventually stopped, and 2 lava domes emerged in January 2021, one on the southwest flank and another near the summit center. That result is an important warning against reading every deforme signal as proof of collapse. A volcano can move significantly, deform permanently, and then reach a new stable arrangement. It is also a warning against ignoring movement, just because the worst outcome did not occur. The deformation showed that magma pressure could mobilize a deep section of the summit, and the lava domes that followed became the sources of continuing avalanches and pyroclastic flows in the years after. The crisis did not end with one giant failure. It reorganized the summit into the system active today. The 2023 collapse sequence shows what a larger partial failure can look like during this kind of prolonged dome building phase. On March 11th, the southwest dome began collapsing in a series of avalanches. During less than 3 hours, 21 lava avalanches generated dozens of pyroclastic flows that moved down the Bebeng and Krasik drainages. Ash rose in dense curtains from the moving deposits and spread across communities downwind. The activity continued the next day. By early March 13th, monitoring reports had recorded 60 pyroclastic flows, most of them directed into the Bebeng drainage. drone services showed that the southwest dome's estimated volume had fallen from about 2.76 million cubic meters before the sequence to roughly 1.69 million cubic meters afterward. Nearly 40% of the estimated dome volume had been removed, and that number reveals why a partial collapse can be dangerous without destroying the whole dome. The summit still contained hot lava. The eruption continued, but a large enough section failed to generate repeated currents, ash plumes, and significant changes to the dome's shape. And the longest measured deposit in the Bebeng drainage ended about 3.7 kilometers from the center of the summit crater. That distance remained inside the official hazard zones used at the time, which is exactly why those boundaries matter. Any dome does not need to explode outward in every direction to create a serious event. Gravity can focus the danger into one valley. This makes collapse direction one of the most important operational questions. People on another flank may see ash but remain outside the dense current path, and communities lie with the receiving drainage face a very different problem. The 2023 event also demonstrates why the phrase next collapse cannot be reduced to one dramatic instant. A dome may fail through a sequence in which the first avalanche changes the slope, a second removes support, and a third exposes hotter material. Pyroclastic currents continue for hours or days as the damaged face readjusts, and the dangerous period may outlast the first images shared online. Merapi's 2010 eruption revealed a much more extreme version of the same basic problem, rapidly changing summit conditions, accelerating magma output, and pyroclastic flows capable of traveling far beyond ordinary dome collapse distances. In October 2010, Indonesian scientists detected earthquakes, gas emissions, and ground deformation far above Merapi's usual activity. Satellite radar was used to track rapid dome growth through the clouds. Authorities initially evacuated people within 10 kilometers. 23 hours later, the first pyroclastic flows traveled about 8 kilometers. Monitoring then showed that lava extrusion was continuing at an exceptional rate. On November 4th, officials expanded the evacuation zone to 20 kilometers. And only hours later, the largest Merapi eruption in roughly a century generated pyroclastic flows and surges that traveled as far as 15 kilometers from the summit. And the 2010 eruption was not simply the collapse of a slowly growing dome like the routine events seen in 2026. It involved rapid magma ascent, explosions, dome destruction, and sustained high-energy currents. That distinction must remain clear. A daily avalanche today does not mean Merapi is repeating 2010. The current report does not describe deformation or gas signals at the extraordinary levels observed before that crisis. The alert remains at level 3, not the maximum level, and current pyroclastic flows have been measured on the scale of a few kilometers, not 15. But 2010 explains why officials do not treat dome growth as a harmless visual spectacle. The eruption showed how quickly the operational scale can change when magma supply, pressure, and summit instability intensify together. It also showed the value of monitoring before the largest event, and the decision to extend the evacuation zone was made before the long pyroclastic flows arrived. Satellite radar, seismicity, gas measurements, and ground deformation provided evidence that the system had moved beyond its familiar pattern. The useful lesson is not that history will repeat on schedule. It is that the difference between routine collapse and crisis can emerge through a combination of signals. Scientists therefore watch for changes in several dimensions at once. And scientists ask whether lava avalanches are becoming more frequent, whether pyroclastic flows are traveling farther, and whether the dome volume is increasing rapidly. They compare those changes with deformation, shallow earthquake locations, gas emissions, and any shift toward a different drainage. And one unusual measurement may have several explanations. A coordinated change across multiple systems is harder to dismiss. This is the second major reframe. The danger of a lava dome is not simply its size. A dome becomes dangerous through the relationship between supply, structure, pressure, and topography. A large dome can shed small pieces for months. A smaller but rapidly pressurized dome can change quickly. A dome inside a stable crater may be partly contained. A lobe, hanging over a steep valley, may need to lose only a limited section to generate a current. This is why scientists cannot announce the timing or size of the next collapse from a single photograph. Even a precise volume estimate does not reveal every buried fracture. A thermal image shows heat at the surface but not the strength of the dome's interior. And seismic signals can identify rockfalls and magma movement but cannot always map the exact failure plane. The dome is both visible and hidden. Its outer shape can be photographed, but its internal weakness must be inferred, and that inference is complicated by constant rebuilding as fresh lava arrives, cools, fractures, and covers older surfaces. Material that appeared unstable may collapse and leave a stronger face. Material that appeared stable may be undermined from below. Every new layer changes the mechanical problem. Result is not random, but it is not fully predictable. Scientists can identify rising hazard. They cannot schedule gravity. The current July 2026 activity therefore sits in an uncomfortable middle ground. Merope is not quiet, is not in the kind of rapidly escalating crisis documented in 2010. The active dome is producing repeated avalanches, and occasional collapses are already generating pyroclastic flows, and that makes the hazard real in the present tense, even though no evidence supports a claim that a catastrophic failure is imminent. This distinction is the core of responsible volcanic reporting. An active dome can remain unstable for a long time. Periods of frequent avalanches may alternate with quieter intervals, and extrusion can continue slowly. Collapses can repeatedly trim the dome without producing a much larger event. The system may maintain this pattern for weeks, months, or longer. The length of the phase does not make the dome safe. It also does not create a countdown. What scientists can do is update the probability landscape as observations change. A sudden increase in dome volume would suggest that magma is arriving faster than collapse is removing it. Accelerating deformation could indicate pressure building beneath the summit. A shift in earthquake type or location could show magma opening a new path. Larger or hotter rockfalls could expose fresh lava. Longer pyroclastic flows could demonstrate that more material is becoming available, or that the receiving valley is becoming available, or that the receiving valley is becoming more efficient at channeling it. A change in several of these signals would carry more weight than any one sign alone. Weather adds another layer. Clouds can hide the summit, limiting visual confirmation of avalanches and dome shape. Heavy rainfall can remobilize loose ash and pyroclastic deposits into lahars that travel through river valleys after the hot flow itself has ended. The volcano therefore creates hazards on different clocks. A dome collapse can develop in seconds, while a sequence of pyroclastic flows can continue for hours. Loose deposits can remain available for later rain-driven floods. The summit event may be brief, but its material continues moving through the landscape. And this is one reason Merope's monitoring system does not focus only on the crater. Observatories watch the dome, seismic network, gas, deformation, weather, and river channels. Local authorities connect those measurements to evacuation routes and exclusion zones. The current Level 3 status tells the public that activity is elevated and that access restrictions must be treated as operational boundaries, not sightseeing suggestions, and the recommended distance varies by sector because the active southwest dome and surrounding topography direct different hazards into different drainages. A 3-kilometer limit in one direction does not cancel a longer 7-kilometer zone in another, and the map must be read by location. That is also why a thumbnail showing one enormous radial explosion would misrepresent the present danger. Merope's current activity is strongly directional. Daily lava avalanches and recent pyroclastic flows have been channeled mainly along western, southwestern, and southern drainages. A better image is a steep summit dome leaning over a valley. The danger is concentrated before it spreads. The final title uses a larger collapse rather than the next collapse for the same reason. Small collapses are already happening, and the scientifically important threshold is whether a future failure involves enough material, heat, and momentum to produce a current that travels farther than the ordinary avalanche pattern. No agency can name the exact block that will detach. No camera can see every fracture. No historical recurrence interval can tell us the day, but the volcano is not silent about its condition. It speaks through repeated rockfalls, hot material descending the slopes, changing dome morphology, seismic signals, and the distance reached by each current. And the task is to listen without turning every signal into a prediction. Merope's 2020 deformation crisis showed that large movement can stop without catastrophic flank collapse. And the 2023 sequence showed that a partial dome failure can remove a major fraction of the dome and generate dozens of pyroclastic flows. The 2010 eruption showed that when multiple signals escalate together, the hazard distance can change dramatically. And those 3 episodes teach different lessons. Deformation is not destiny, partial collapse can be substantial, and escalation can outrun familiar patterns. The current activity must be judged on its own evidence. As of the latest report available for the script, the evidence shows continuing eruptive activity, daily lava avalanches, one detected pyroclastic flow during July 16, 22, alert level 3, and location-specific exclusion distances of 3 to 7 kilometers. It does not show a newly formed 2020-26 dome. It does not show a forecast date for a major collapse. It does not show that Yogyakarta is facing an immediate citywide disaster. It shows an active dome continuing to shed hot material above a densely developed volcanic landscape, and that is serious enough. The next important observation may be a drone model revealing a newly oversteepened lobe. It may be an increase in shallow earthquakes. It may be a pyroclastic flow that travels farther down a drainage. It may be a period of reduced activity, showing that supply has slowed. Each result changes the interpretation. None should be read alone. This is what makes lava dome crises difficult. The structure grows slowly enough to watch, yet individual failures can move too quickly to escape after they begin. Monitoring cannot stop gravity. It creates the time needed to keep people outside the paths gravity is most likely to use. Picture Merapi before sunrise, and clouds drift around the summit, hiding parts of the dome. Through a break in the weather, a rough mass of dark lava sits on the upper southwest flank. The outer blocks have cooled, but cracks reveal a red glow inside. One fragment breaks free, it strikes another block and divides. A chain of incandescent rock begins moving down the slope, following the same valley that has received hundreds of earlier avalanches. Most events stop high on the mountain. This one may stop too, but above the moving rocks, the remaining dome has changed shape again. A small support is gone, a fresh face has been exposed, and new lava continues pressing from behind. The avalanche disappears into the darkness, but the dome remains above it. The next mechanical test has already begun.